This is Mr. Craig, and I want to discuss the answers to the homework from day 100, Kinetics Part A. Very similar to the examples that were in the earlier videos. Here you're given a set of conditions, experiment 1, 2, and 3, and you're given the concentrations for A and B, and then you're given the initial rates for each of the two trials. Part A says, what is the rate law? Well, when we first start off, we want to write out, again, the word rate for the rate law, and K is our constant for this whole reaction. Doesn't matter what the concentrations are, the K will remain the same. And we are unaware of what what the order for A and B happen to be in this situation. So what we want to do is start off by picking two trials. In this case, it looks like I'm going to start off with these two have the same concentration, so I'll start off with experiment 2 and 1. And again, you don't have to start off with that. You could have started off with 1 and 3 if you so desired. So the first thing that we want to do is check out the rates of the two reactions here. We want to put rate 2 over rate 1, and again, it doesn't matter which one in this case, especially since the ratio is the same, even though the concentrations are different. So that should tell you something real quickly here. Once I have what the rate is equal to, now what I want to do is plug in the concentrations by plugging in the values or the concentrations for these concentrations for A and B. And let's cancel out anything that's alike. So the K's actually get canceled out as well on this, while the two concentrations that are 0.2 also get canceled out. So we're left with 0.8 over 0.4 to the m power. And again, we don't know what m is. We're trying to determine what that order is. So we have 2m. Okay. And then that's been reduced down to that. Since our rate was 1 and we have 2m equals 1, then the order for this reactant, or for A, for A, has to be a zero order reactant. And what that means again is that regardless of what the concentration is, the rate will remain the same. And in this instant here, the concentration was doubled while the other remained the same, so we doubled the concentration, yet the rate remained the same. And how do we know that? Because somebody went into the lab and timed it for you. So we determined that for you experimentally. Alright, so now we can look at experiment 3 and 1, because the concentration for A happened to be the same. And if we can have that scenario, let's go ahead and use that. So we're going to look at this, and let's put the faster of the two rates on top. So it looks like we want to have experiment 3 over experiment 1. So by doing that, we do the calculation, and it comes up that we have a value of 4, which means that experiment 3, or trial 3, is 4 times faster than experiment 1. Go ahead and look back at your concentrations, plug those values in, and let's solve for n in this case. So we cancel out all like terms. The constant is canceled out. The concentration for A is canceled out since it's 0.4. And then so we have 0.4 over 0.2. And again, this 4 right here is from this 4 here. So when we take 0.4 divided by 0.2, that tells me that I had twice the concentration, yet the rate is 4 times faster. Therefore, my order must be 2. In other words, 2 to the second power equals 4. So when I write out my rate law, this is what I have, where rate is equal to K to A to the 0 power times B to the second order. Or, if you so choose, you do not have to include A to the 0 power. That's why in this second example here, you don't see A. Again, anything to the 0 power is equal to 1. The unit turns into a 1. The number, the concentration, turns into a 1. So you may show it as the first set here, or as the second way. Okay. However, be sure to show your work. Once we have our rate law, let's determine what the rate constant is. So again, we'll rearrange the variables so that the rate's on top and our concentration for our reactants are on the bottom. And I so chose to leave A out since it would be to the value of 1. Do show your units on this. And in this case here, we will have 1 over molarity seconds. So this molarity gets canceled out. This one also gets canceled out. Oh no, I'm sorry, to the second order. So only one of the molarities on the bottom gets canceled out while the one on the top gets canceled. So we have 1 over molarity squared. Second, and then typed in that value. Sorry about that. Looking at number 2, again, we want to try to find where the values or the concentrations are the same. So it looks like in experiment 2 and experiment 1, and then in experiment 3 and experiment 2. So first of all, write out the rate law. And again, we don't know what the orders are yet, so we have to determine that through math. So it looks like I'm starting off with these 2 concentrations here, so I need to start off with those rates. So I'm going to put the larger of the 2 rates on top just to make it a little easier. If you want to have it the other way, it's not a problem. This will all work out the same way, mathematically speaking. So I want to plug in the concentrations for the respective reactants, and then reduce anything that's alike, and then solve for, in this case, N. So it looks like I doubled the concentration and the rate is doubled, therefore that is the qualities of a first order reactant. Looking at the next scenario here where I can look at these 2 here. So in experiment 3 and 2, I plug in my rates, and again, I went ahead and put the larger of the 2 values on top. So in this case, experiment 3 or trial 3 is 4 times faster than trial 2 or experiment 2. Go ahead and plug in those values, and again, cancel out alike terms. So now that we have, and again, this 4 comes from this rate right here, double the concentration, the rate becomes 4 times faster. That is the characteristics of a second order reactant. So when we go ahead and plug in the orders for our rate law, we notice that the nitrogen monoxide is the second order reactant, and it won't always be. So it depends on the reaction. So don't automatically say, oh, and anytime I see nitrogen dioxide or monoxide, that it's going to be a second order reactant. Depends on who it's reacting with as well. The chlorine is a first order reactant, and I put a little note here. Notice that the exponent 1 is not shown, however, it is implied. So once I have my rate law, now I can determine my constant, and in this case it equals 180, and my units in this case, these 2 molarities here will cancel out. I'm left with molarity squared second. So it's 1 over molarity squared second. Looking at question number 3, I made it a little more interesting. Notice the balanced equation. That's a humdinger. I would definitely cross that out right off the bat. I wouldn't even focus on that at all. Don't even look at the balanced equation and say, oh wow, I didn't know we had a fifth order reactant. We don't. We have a 0, a first, and a second. So don't let the balanced equation even cause you to look at it more than once, and just other than you going, wow, that's pretty cool. Move on. So again, we want to look at our table and try to find alike concentrations, and notice that I have 3 reactants here, and that's fine. That's okay. There's nothing wrong with that. Try to find the experiments that have the same concentration. So for the bromate, it looks like we're going to have experiment 2 and 3. For the bromine, we're going to have experiment 1 and 2. And for the hydrogen, you get to pick. Looks like you might want to go with maybe 1 and 3 or 2 and 3. Well, it depends. So we want to be able to make sure that the other concentrations change. All right, so our rate law looks like this. We don't know what it is yet. So MNP sounds like a good one. If you want to go XYZ, that's fine too. We'll go ahead and determine the order for each of these. So it looks like I started off with experiment 2 over 1, which means that the concentrations for the bromine and the hydrogen are the same, while the concentration for the bromide is actually twice as much. So the rate is twice as much, the concentration is doubled, therefore that is a first order reactant. So my bromide is a first order reactant. I went ahead and looked at some more here. Looks like I'm doing 3 and 2. So again, take those rates, divide it by each other, and in this case here, the bromide and the hydrogen have the same concentration, while the bromide ions have different concentration. So again, twice the rate is equal to twice the concentration. That is also a first order reactant. And then let's try to find a scenario where the first 2 reactants have the same concentration, where the hydrogen has different concentrations. And in that case, it looks like we have experiment 4 with experiment 1. So again, the rates in those two cases make it, or state that experiment 4 is 4 times faster than experiment 1. And then when we go ahead and look at the concentrations, it's only double. So that is a second order reactant for the hydrogen. So my rate law looks like this, where the bromite and the bromine have first order reactants, and the hydrogen is a second order reactant. I can determine the constant K by rearranging the variables, plugging in the concentrations for any of the experiments, and it looks like I may have chosen the which one did I pick? So 0.1, 0.1, 0.2. So it looks like I chose the last one, experiment 4. And again, it does not matter, just as long as you plugging in the concentrations for the respective rate. So regardless of which trial you chose, you still should have gotten 8, where the unit is 1 over molarity cubed second. Hope this video's helped. I hope these types of problems are not difficult to you. They are very, very tedious. But again, I'm anticipating that we'll see this year on the AP exam.